Hi everyone, my name is Jianshuo, and I'm gonna share about our team's work, time travel, real-time timing, drift attack on system time using acoustic waves. This is a joint work with the Chinese Academy of Sciences and Virginia Tech. In this work, we review one physical vulnerability of real-time clock circuits, and the malicious user and make a device's internal timestamp run fast or slow without touching it. I believe everyone may have faced or used many kinds of embedded devices with timing, measuring, or scheduling features, like using industrial PLC devices to perform manufacturing pipeline schedules, or use medical devices to record patients' vital signs accurately. Or you may simply use IoT Hub to schedule timed tasks for paired devices. Those devices usually adopt a real-time clock circuit to generate timestamps. An RTC is a device's wristwatch. RTC consists of the crystal, a battery to provide energy, and a microcontroller to store timestamps. The quartz crystal oscillator generates periodic and stable sinusoidal waves. When the amplitude of signal generated by crystal reaches to the threshold, the time digit counter in microcontroller increments by 1. The crystal oscillator is a core component of RTC circuits. RTC uses a tuning fork-shaped crystal oscillator to generate oscillation signal, as shown on the left side. RTC is equipped with the crystal with a resonance frequency of 32.768 kHz, covered in the metal can, and the plated electrodes are attached on both sides of the crystal surface. When it flexes, the piezoelectric effect creates charge. Electrically, the crystal sits in a piezo oscillator with an inverting amplifier and two load capacitors, behaves like a very high Q inductor. When an external AC field or stress arrives near the crystal's natural, the plate resonates and deforms slightly, generating extra charge on the electrodes. Because the crystal is very high Q, even tiny physical energy like vibration with the same frequency as a resonant frequency may produce noticeable electronic response. So, many devices rely on accuracy of timing. For example, if the RTC doesn't work properly in manufacturing pipeline, devices like the robotic arms and industrial motors won't collaborate properly. Therefore, it may result in abnormal products being processed. So, it is possible to modify the timing in a contactless, non-intrusive manner. This work aims to reveal new security vulnerability that the timing accuracy in RTC circuits is vulnerable to be interfered, leveraging crystals' piezoelectric effects. So, to make sure that the attack strategy to be practical, we assume attacker can only infer targeted devices' RTC working conditions by observing liquid EM signals and perform close proximity, non-intrusive attack nearby. So, how did we try to achieve that? We first attempted to exploit the crystal's acoustic resonance by using an ultrasonic speaker tuned to its resonance frequency, hoping to induce oscillation. But This had no effect on timing, and the magnetic probe measurements showed no waveform change. We later realized that ultrasound can hardly penetrate the crystal-sealed metal casing from the air due to the large acoustic impedance mismatch. Then we tried different approaches and found that at certain moments, placing a piezo transducer against a solid surface near the hardware, such as a laptop, and emitting line waves seems to halt the time updates. At the same time, we observed several glitches at the RTC crystal. This happens because acoustic waves propagate through solid media with much lower impedance mismatch, causing the additional vibrations in the crystal. The ceramic transducer emits ultrasonic vibration through the solid materials, letting the energy propagate to the location where RTC crystal is at. Assume that the ceramic transducer vibrates in the sinusoidal form with a frequency of omega and initial phase phi, given a solid material with a thickness of x and a target location with the horizontal distance of z to the transducer will experience a vertical vibration with the form of uxt. We could look at the real part of this function, which follows the sinusoidal form with the same frequency as the transducer vibrates. Since the RTC crystal is in close contact with the solid surface, we can approximate that the RTC crystal will vibrate up and down at the same frequency. Since the acceleration is the second derivative of displacement, according to the piezoelectric effect, we know that this vibration will induce additional electrical resonance, and the frequency is comparable to a mechanical vibration frequency. We also discovered an interesting phenomenon. When we intermittently send vibration signals with different initial phases, the EM signals from the crystal show the corresponding phase shifts. Recalling how the RTC keeps time, this led us to the core idea behind changing the timing rates. By intermittently emitting line waves with specific initial phases, we could induce additional resonance in the crystal, shifting the edge trigger moments and thus altering the timekeeping. Based on this, we propose an attack method that alters the RTC's timing rates via crystal resonance. First, the attacker can offline test different solid materials to build a database of the attack parameters. Specifically, the attacker can look up longitudinal and transverse wave speeds, CL and CT, based on different solid materials. Those two parameters are important for getting the value of parameters alpha and beta. After that, we also need to calculate wave number Ka from guided wave equations as shown in the left side. The vibration form is sinusoidal, and amplitude lambda and phase phi can be derived. The attacker can then offline test different solid materials, observe the phase jitter delta after attack, and further to build a database of attack parameters. Because the attacker previously tested the phase jitter under different attack parameters, during a real attack, the attacker can passively log into the RTC with a small H-field probe and estimate the instantaneous phase of the crystal oscillation. If the target time drift T, we look up phi and the per burst jitter delta from the table, then compute the plan, number of the burst K, burst duration T1, and the interburst gap T2. Since one burst advances the clock by roughly delta over 2 pi f0 seconds, we may choose the K approximate to the scaling of T multiply 2 pi f0 over delta. Then, when the measured phi enters our launch window, we transmit the burst with the required initial phase. After each burst, we repeat the closed loop to stay aligned. The burst injects control phase jitter at the crystal after the oscillator's filter and edge detector. Those phase nudges become earlier or later threshold crossings, accumulating into the intended forward or backward drift. As a rule of thumb, thinner surface couple better because fewer bursts are needed. Based on the finding, we validate the attack on a variety of RTC modules, development boards equipped with RTC, and 2 commercial devices. We tested these modules by selecting the corresponding attack parameters for various forward or backward drift amounts and repeating each test 100 times. The success rate was no less than 78%, showing that this vulnerability exists in many RTC modules. We also studied the robustness of the attack. First, the medium thickness. We can find from the graph that the thicker the solid medium, the more difficult the attack is. From the second part, we can see the magnetic sensing distance, the effect of that over the attack success rate. We can see that the attack success rate is over 70% when the probe is within 5 centimeters of the crystal. Then, with the obstacles and the clutter, we found that nearby obstacles have little impact on the attack success rate. So for the details, please check the paper. We further tested some more practical factors. First, materials properties matter. Some materials, notably soft, lossy polymers or thick rubber, require noticeably more drive energy to induce the same phase shift compared with the rigid, thin solids. When you profile service offline, we would recommend you mark those that need higher amplitude or longer bursts. Besides, when launching the attack in real-world scenario, we may first get to know about the model of target devices, then prepare for suitable attack parameters. We use a 6 BP monitor as example. We collect the EM leakage data under different probing distance, then train a deep learning classification model. We then prepare some testing EM signals and get the model classification accuracy. We found that under our current physical settings, probing is generally effective within 5 centimeters distance, which means that over 50% of success rates. We then further evaluate the effectiveness of the attack on commercial devices. When launching the attack on commercial BP monitor at different attack vectors, we found the BP monitor responded with different ratings. That means that crystal may experience different extents of phase jitters. We also briefly test a kind of mini pulse machine, and the timing drift results can be referred to our paper. So from this work, we can know that attacker can leverage the acoustic vulnerability of the crystal oscillator to manipulate internal RTC timing. To defend against this kind of attack, the key point is to disrupt the energy being propagated to the crystal or avoid the frequency of attack signal aligned with the crystal oscillation frequency. So the manufacturer can use crystals with higher frequency, maybe on megahertz level, accompanied with PLL divider to adjust the output frequency to around 32.768 kHz. Because it is typically hard to generate ultrasonic vibration falls into a range of megahertz, so those kind of crystals won't be affected by this kind of attack. Besides, one can place shock-absorbing materials like sponge rubber around the crystal to protect the crystal from being affected by radiation energy. So, in a nutshell, this work, we found guided waves can affect RTC crystal's oscillation by applying signals with different initial phases to induce additional resonance. The edge triggering moments can be changed, thereby affecting the RTC timing rates. Then we conduct extensive experiments to test the effectiveness and robustness of this kind of attack. More details, please refer to our paper. Thank you for listening.